Hello everyone and welcome again to the second part of the Haskell tutorial. In our last video we took on a puzzle. It's the so-called short problem, and we learned how to present this problem in Haskell. And unfortunately we had to guess. We only were able to check the solution, which was a guess, and to show a pretty print of the solution. But in our case, this is not what we want because we are developers, or as the ex-CEO of Microsoft used to say, developers, developers, developers. So right now we should find a way to generate a concrete solution with an interesting function. Just a quick reminder of what we did. We were showing we developed the LD2 file, which stands for linear Diophantine equation with two variables. We create the type solution2, and we had two functions, check solution and pretty print. Let me show them quickly. So quickly reload and then quickly saying pretty print, the simple problem. And the simple problem was having the following solution, which was 1 and 3 and 0. So the pretty print LD2, this is how it's going to print it. And then to check it, it was supposed to say 1 0 here, and then simply check whether it would be working. No, it wasn't like this, so it was 3 and 0. Yeah, set 3, and this is how it worked. Okay, this is what we had so far, but now we should find a way to create our own solution without guessing, because as I mentioned, we should be able to write a solution or a function for a solution in Haskell. So without further ado, let's continue. How are we going to do it? Well, this is probably one of the oldest algorithms in the world. So we should find a way to resolve this one. A times x plus b times y equals c, considering the fact that everything here is a whole number. And fortunately we can use the Euclidean algorithm that finds the greatest common divisor of two numbers. So for example, the greatest common divisors of 10 and 50 is 10, just in giving you a hint, and the greatest common divisor of 18 and 11 is, yeah, in this case 1. So the second part of the algorithm is pretty much not only to find the greatest common divisor, but to find also two magic numbers that are going to be named x prime and y prime, that are going to say that a times x prime plus b times y prime are going to give us d, and d in our case is going to be the greatest common divisor. So in order to find the x prime and the y prime being equal to the greatest common divisor, we have to solve something called the Bézout identity, and this algorithm gives us x prime and y prime, so it can make this one true. So what do we have to solve? This one here, in order to get this one here, in order to get some result other than the one that we had for similar functions and equations. Okay, let's think of a way how to do it. pretty much there is something in the Bezos identity called scaling factor, and it is k. So the idea is that we multiply the whole equation, a times x prime plus b times y prime by k times the whole equations, and then pretty much it's equal to k times d, because we had it like this. So the idea is let me explain better. We multiply k by here from the left, and we multiply k to the right like this. So this is like a simple mathematical rule. If you multiply an equation with the same number from the left and the right side, it should not be changing. That's the truth. So what do we have further? A times k times x prime. This is by design, pretty much here, this one, plus b times k times y prime equals c. This is this one, yeah. Pretty much a bit differently written, but it is what it looks like. And now, simply like that, we should be having our answer. If you are wondering how I get c from k times d, by design, this scaling factor k is actually something more. It is c divided by d. So here, yeah, this is pretty much how it goes. So solving this one is a c. So we have it like that. Pretty easy to explain, I would say. And the solution of x and y we are looking for looks like the following: x equals k times x prime, and y equals k times y prime. Yes. If you are still wondering how we get c from k times d, then imagine the following. Actually, k times d can be replaced with c times d, and c times d like this, times d. In this case, d and the other d can be removed, so we only get a c. Okay, probably it would have been easier if I have written it with the snipping tool. So it was something like c times d times d, and because c times d is what is k by design here, c times d equals k. So we had like k times d, and then we neutralize these two, and then we get simply a c. So that's why k times d equals c. Just FYI. Hope you understand it so far. And now let's continue. That's pretty much the plan that we have to implement into Haskell. And now it is time to code. So let's go to our beloved Haskell and see what we can do here. Okay, so first, implementing the extended Euclidean algorithm, and it's going to be a classic recursive function taking two integers, and we need to return three things: the GCD and the magic numbers x prime and y prime. And so we're going to return them into tuple, and this is how we're going to name it: extended Euclid. And then we have integer, integer, and then three integers. So taking two integers, returning three. As I said, taking A, B, and GCD of D, or GCD simply, which is going to be named D, and then returning taking A and B and returning GCD experiment Y prime. This is what we are going to do. Exactly. Yeah, thanks for listening so far and bearing with me. So, as I mentioned, this is going to be a recursive function, and we need a base case. So the base case for this algorithm is when B is 0. So if B is 0, then the GCD of A is what exactly? It's an A. So something like this. You see A0, A1, 0 should be working. Why something like this is working? The idea is that, yeah, this one is A, the one that we are giving, this one is 1, this one is 0. So let's try to explain it better. So just to follow, here we are having something like AX prime about this function here, plus 0 times, I'm staying consistent here, 0 Y prime equaling A. And if X prime equals 1 and Y prime equals 0, then it should be working, considering the A times 1 plus 0 times 0 is equal to A. So this is pretty much the base case that we are trying to model here. A and 0 returning A, 1 and 0. I really hope you understand it. Let me continue once more. Let me repeat it once more. A0 here, A0 here, and returning A, 1 and 0. So as I said, this is the base case, the base case of the recursion. So now let's try the recursion step. We're going to call the function on B and the remainder of A divided by B. Then we'll use the results to find our new X and Y. I'm not going to prove why these steps works. It's just theory. It's a math theory, and we only have about 30 minutes to solve this one. So let's continue here. On extended Euclid and AB, that's correct. And I think almost everything that it works and proposes is correct, because these are like basic functions. I'll just use our names. Here, just letting you know, for Haskell, this prime here is actually like the normal way just to use a function. So Y prime, or whatever you're calling this, apostrophe. So extended Euclid B equals A mod B. A mod B is something interesting. I'm just going to show it here. For example, 7 mod 5, and it gives 2. So 7 divided by 5 is actually 1, and 2 in so-called in reserve or in mod. If we say 8 mod 5, it would be 3. So you got the idea of the mod. Okay, X equals Y prime, and Y equals X prime minus A divided by B times Y prime, and we are using D and then XY. This is pretty much the beauty, and that's the entire algorithm. So the let in block, actually this is the way to get the results from the recursive call here. And we calculate our new X and Y from them. And now it's probably a good idea to test it, reloading. Okay, it asks for some G. I haven't saved. Control S again, reloading, now it works. Okay, So let's try the simple problem. Let's see whether we have it. Pretty print simple problem. Looks like this. Yep. And we need the GCD of A equals 1 and B equals 4. I guess it would be easy to see what the GCD is going to be even without this. But the idea is to see. Okay. Extended Euclid. And somehow extended Euclid ask for some data or something. And after some research on why I have entered, or why we have entered endless recursion, the answer is that we never hit the base case, and we didn't hit it because there is some misspelling here. On extended is written like this. So just double checking on everything, pressing Ctrl S, pressing G, pressing CD, and then I think we were in examples, and then yes, then pressing GHCi.LDHS. Yep. GHCi. Okay, so let's load LDE, or just exit. I have never showed how we quit the GHCi. In this case, it is like just quitting LDE HS. And now let's try the extended Euclid with 1 and 4. Now it should be working. Yes, it is 110. What is this 110 giving us on the 1,4? It is pretty much saying that D is 1, X prime is 1, or something like this. X prime is 1, Y prime is 0, and here the D is also 1. So the idea is we have 1 times 1 plus 4 times 0 equaling 1. So 1 and 4, this is what we have submitted, and it gave us 1 and then 1 and then 0. Well, it works. Let's try it with the short problem where we had 18 and 11, and let's see what is going to be received. Well, it gave us 1 minus 3, 5. What does this mean 1 minus 3, 5? Well, the 1 is the result. The X prime is the minus 3, and Y prime is the 5. So let's do the math. So we had 18 times minus 3 plus 11 times 5 should be equaling 1. Is this correct? Fortunately, we have Haskell, and we can do it like this. It says true, and if it didn't say true, we can do it like this again. So this is true. It means that this fancy extended Euclidean algorithm is working. So let's try with a concrete function, because this is not yet the answer, but we have the Euclidean function that is actually a step towards the answer, a step in the right direction. So let's try the concrete solution function. So how do we make it? We should be taking the LDE2, and then we should find a way to do it. Exactly. How do we do it? the problem here is that it doesn't always return a result. So we here should be introducing one of the most important types in Haskell, which is pretty much called maybe. So a maybe can be just a value, or it can be nothing, and just and nothing are also important types in Haskell. So we have maybe, just, and nothing. So let's call maybe solution 2. This is what our result would be. So it would be of type solution 2, and solution 2 is this one. So type solution 2 would be integer, integer. Exactly, and our concrete solution would be of type LDE2, and it'd be maybe solution 2. Exactly. So yes, we define solution 2 as type alias, but before defining it this way, let's make sure that we are actually copying our things like that, and there should be no mistakes further. Yeah, so now let's write the function. We have the concrete solution function, and it should be something like this. Okay, LD2, and then A, B, and C, and then equals, and I'm pretty sure that the hints here are really great. Let me see, how can I get them? Control E to continue with Copilot. Copilot is actually cancel, close, doing great stuff. Let's just examine the thing, whether it is. Okay, let D, okay, X, Y, I mean, it would be X prime in our case, Y0 would be Y prime, just because we can do it, but obviously Copilot doesn't like it. Extended Euclid A and B, that's perfect. So in, I'm just going to remove it like this. So in, and then if, and then something like this. Okay, if C mod D is different than 0, then nothing. Else let K equals C divided by D. And when I mean divided, you know what I mean. I mean the thing here, somewhere where I showed it, pretty much 7 div 5, so to say, answering how much is the whole division. So how much do we have? 5 divided by 7, 0. So 7 is contained in 5 0 times, and 5 is contained in 7 1 time. Okay, so C divided by D, and then we have, I'll write it a bit better, and it already knows X prime equals X prime times K, top, and Y prime is Y prime times K, in just X0 and Y0, but I don't like X0. I'm using X prime and Y prime. Should be okay. Example usage. Okay, not Copilot is helping me too much here. Okay, so once more, let's take a look at the concrete solution. So we pattern match to get the A, B, and C here from the LDE2. Sorry for the disruption. We use let block to call our new extended Euclid, this one here. And with this function, we get D, X prime, and Y prime from the extended Euclid, this one here. returning us dx and y. In our case, we renamed them to dx prime and y prime. And we have our guard in the if, so to say, with checking that the c mod d is not 0, because if the remainder is not 0, then the c is not divisible by d. This is pretty much the rule. Let me show you what I mean here. If 10 with remainder 5 is 0, so 10 is divisible by 5, but if we have 6, then we have a problem. It's no whole division. And in the else case, everything is solvable. So in the else case, we are happy. So here we just start with a new let block to calculate the scaling factor, which was this one here, if you remember, here, which was c divided by d. And in this case, the things were a bit more interesting. So to say, scaling factor here, I can even put like a comment or, okay. So comments are like this, scale factor, I'm impressed. I mean, you already knew what I'm going to write. Yeah, this is one of the bonuses when you get with the famous algorithms that are over 1,000 years. Like the machine has learned a lot on them. So after the scaling factor, what do? We found our final solution of x prime and y prime, pretty much. And we finally wrap it up in a just. So let's try to reload. No modules loaded. I don't know how this thing came there. Type solution to integer. This thing is going to be reduced. Okay, I got it once before when we made a solution, the error. This is how it happened. Okay, reload, everything works. And now let's try to see, okay. We have the simple problem already defined here and the short problem already defined. And let's try to see concrete solution of the simple problem without passing anything. And I think we just hit an endless loop somewhere. So let's give it a try for me to fix it. And this time the simple loop was fixed quickly with a Control-C. Concrete solution, extend it. Yeah, it should be working actually. Question, why is it not working? Pressing Control-S quite a lot of times and reload. Concrete solution to simple problem, just x prime, y prime. Okay. Control-C and research. And after a quick research, we found out that we should be using something like this. So to say, not simply returning the x prime and the y prime, but returning what should be returned in the just. So, okay. So Control-S, a lot of times reloading everything and pressing concrete solution, and we get just 3.0, which is actually, I guess, a solution of the simple problem. Pretty much a solution of that one. 1x plus 4y equals 3. You see 3 and 0 are solutions, which is good. Matching the document. And finally feeling good when something that we do actually works. What about the other one, the t-shirts? So we had 18 of the one plus 11 of the other equaling 1188. And it was described here. Let's give it a try. Concrete solution and short problem. Well, Yeah, this was a bit unexpected, but I guess it works. So instead of buying, if we are selling t-shirts and we sell 3,564, we can buy 5,940, which is not that bad, I guess. Let's use the check solution with this number. I'm just curious, check solution. So minus 3,564, comma 5,940, and short problem. Yep, it works. Let's see whether it's a glitch. No, it's not a glitch. It works perfectly. Yeah, it is a solution, and it is true. So the concrete solution function worked, and it find a solution. The problem is that somehow it's not a good idea to buy minus 3,564 shirts. It would be quite a challenge. But the thing is that the Euclidean algorithm doesn't actually promise to find the nicest solution for you. It just promises to find one solution, and in this case it found this one. So anything can be a solution. Our 66.0 here from before is also a solution. This is our previous, I think it was 0,108. And actually, if you want to buy shirts, you wouldn't be happy with either of these three solutions. Probably not with this one. These ones are okay-ish to know the corner cases. But the thing is that all the solutions are part of the solution space. So yeah, our work is not done. But the question is no longer what is a solution. The new question is how do we get from this solution here to a nice solution like 66.0, which is something. So the best way is to generate all the solutions and say what is nice, what is not nice. But in general, this is going to be for another video. This one is already going and taking too long. So let's make a recap. What did we do? We used extended Euclid, which actually was used for solving x prime, y prime, and the GCD. Then we used concrete solution that actually gave us a solution. We learned how to use maybe. I'm not sure that we all learned how to do it, but it is used here, so maybe. And we successfully found a solution for the puzzle, so to say. Probably in a next video, if you are really looking into it and I received at least 2 comments about it, I would write a function that actually shows all the solutions possible, but this would happen later. So that, my friends, is everything so far. Let's keep on programming with Haskell and enjoy the rest of our days. Goodbye and take care of yourself.